Infinite series. Consider the decimal 0.3333 etc., which can be written as 0.3 plus 0.03 plus 0.003 plus 0.0003 plus etc. We have 0.3 can be written as 3 by 10, 0.03 can be written as 3 by 10 square, 0.003 can be written as 3 by 10 cube and so on. Therefore, the decimal 0.3333 etc. can also be written as 3 by 10 plus 3 by 10 square plus 3 by 10 cube plus etc. Whenever we have a series of the form u1 plus u2 plus u3 plus etc. plus uk plus etc., we have this expression will be known as infinite series, and u1 is the first term of the infinite series, u2 the second term, u3 the third term and so on. We have u suffix n or u suffix k will denote the general term of the infinite series. The basic difference between infinite series and sequence is that sequence is just a collection of terms following a particular pattern, but infinite series or series is sum of terms following a particular pattern or a well-defined order. Now let us focus back on this equation 1, which is representation for decimal 0.3333 etc. If you call S1 equals 3 by 10, S2 equals 3 by 10 plus 3 by 10 square, that is S2 equals sum of U1 and U2, S3 equals 3 by 10 plus 3 by 10 square plus 3 by 10 cube, that is if you call U1 equals this fraction, U2 equals this fraction and U3 equals this fraction, which are the first, second and third terms of the infinite series, then we have S3 equals sum of U1, U2 and U3. Therefore, S4 will be sum of 3 by 10, 3 by 10 square, 3 by 10 cube and 3 by 10 raised to 4. Proceeding like this, we will have S suffix n equals 3 by 10 plus 3 by 10 square plus 3 by 10 cube plus etc. plus 3 by 10 raised to n, considering n terms, that is Sn will be sum of u1, u2, u3 plus etc. up to un. Here for this particular series, notice that common ratio equals 1 by 10, which is obtained by dividing second term with the first term or third term with the second term. If you wish to find out the sum of this infinite series, that is we wish to find out the value to which this representation will converge to. For that, we can make use of this expression Sn, which is sum of n terms of the infinite series. We have, when Sn is multiplied using 1 by 10, it becomes 1 by 10 times Sn equals 3 by 10 square plus 3 by 10 cube plus 3 by 10 raised to 4 plus etc. plus 3 by 10 raised to n plus 1. When you take the difference between these two expressions, that is when you consider Sn minus 1 by 10 times Sn, we will have only two terms remaining after we have cancelled the common terms. We will have Sn minus 1 by 10 times Sn equals 3 by 10 minus 3 by 10 raised to n plus 1. The LHS can be rewritten as 9 by 10 times Sn, taking LCM here, and in the RHS, when you take 3 by 10 common outside from both the terms, it becomes 3 by 10 times 1 minus 1 by 10 raised to n. Since we wish to find out the expression for Sn, we will take 9 by 10 as reciprocal to the RHS, so that we will get Sn equals 1 by 3 times 1 minus 1 by 10 raised to n. We have evaluated this expression for Sn in order to find out the sum of the infinite series 3 by 10 plus 3 by 10 square plus 3 by 10 cube plus etc. up to infinite terms. We have this infinite series 3 by 10 plus 3 by 10 square plus etc. up to infinite terms, which is equivalent to 0.3333, is exactly equivalent to limit n tends to infinity Sn, because Sn considers sum of first n terms of the infinite series, and when you let this n to tend to infinity, it is equivalent to this infinite series itself. We have limit n tends to infinity Sn equals this expression, and we have found that 3 by 10 plus 3 by 10 raised to 2 plus 3 by 10 cube plus etc. 3 by 10 raised to n, which equals Sn, can also be equated to this expression. Therefore, the infinite series 0.3 plus 0.03 plus 0.003 plus etc. up to infinite terms is equivalent to limit n tends to infinity 1 by 3 times 1 minus 1 by 10 raised to n. 1 by 3 can be taken outside the process of application of limit. When you give limit n tends to infinity to this term 1 minus 1 by 10 raised to n, we have 1 by 10 raised to n becomes 0 on application of limit n tends to infinity. Therefore, we have the answer for this expression will be 1 by 3 itself, which means that this decimal 0.3333 is equivalent to expression 1 by 3, or this infinite series or equivalent infinite series will converge to the sum 1 by 3. The expression Sn, which denotes sum of first n terms of the infinite series, is known as nth partial sum. And when you consider the sequence of partial sums, that is sequence Sn denotes S1, S2, S3, etc., Sn, etc., where S1 equals U1, S2 equals U1 plus U2, S3 equals U1 plus U2 plus U3, and so on. This sequence will be known as sequence of partial sums for the infinite series. For any infinite series, we can find the corresponding sequence of partial sums. For the infinite series that we had considered, which is 3 by 10 plus 3 by 10 square plus 3 by 10 cube plus etc. up to infinite terms, we have the sequence of partial sum will have first term which is 0.3, second term will be S2 which is having the value 0.33, third term of the sequence of partial sum will be S3 which is the sum of U1, U2 and U3 which has the value 0.333 and so on. The idea of infinite series originated when mathematicians tried to rewrite such infinite decimals as sum of infinite number of terms whose nth partial sum will help us to find out the value to which this infinite decimal will converge. Since every infinite series summation un will have nth partial sum as well as sequence of partial sum, with the help of behavior of sequence of partial sum, we can easily find out the behavior of the given infinite series.